All right, today's lecture, and hopefully this won't be too long, it shouldn't, is primarily on significant digits. Significant digits is just a fancy way for saying when we have a measurement in science, how precise is the measurement? Okay, how many units of precision do we get from whatever device that we're using to take a measurement or a data point? Now, if I drop down to number 2, there are two key words that are often used interchangeably, but they're not the same thing: accuracy and precision. The easiest probably way of thinking about this is an example. Let's think of a bullseye. In a bullseye, if we're going to be shooting at a target, okay, and if we are accurate, and when I'm shooting at something, you'll notice that it says refers to how close a measured value is to accepted value. So, an accurate would be where when I shoot it, that I hit the target, okay, I just shot it 4 times, that I'm shooting right around the bullseye. That's a sign of accuracy. If I'm shooting free throws, it'd be like your percentage. How many makes, how many times when you shot the ball did you make the shot? If that's going to be what we want, the measured value. Okay? Precision is how close a series of numbers are to one another. So what I have here in this bullseye, the first one I drew here, is both accuracy and precision, and this is why they're often used interchangeably. However, we can have a precise instrument or precise measurement being done, but it's not accurate. A great example of this would be if I have that bullseye again, and if I have my gun and I shoot at it from, let's say, 200 yards, and I shoot 4 times, when I'm aiming at the bullseye, my 4 shots from 200 yards are in a very tight circle. Let's say it's an inch or two. The gun and my shooting form is showing consistency. I'm very precise. I'm constantly hitting in about the same area. But this is not accurate. So this is showing precision because the repeated numbers are in the same spot. But it's not accuracy because it's not where we want the shots to be. So this occurs when, if you're shooting at a target, that your sights are off. So if I were to move my sights, okay, and move it down and maybe over to the right a little bit, now it again hit where the bullseye is, and now that's both precision and accuracy. So accuracy is how close we're getting to the accepted value. Precision is when I do the trials multiple times, I'm getting close to the same number each and every time. Okay? So when we look at instrumentation, the precision of the instrumentation comes down with the number. In one device, I might be able to measure in a scale, in mass, I might be able to measure the mass of something to be 2.5 grams. We would say that this measurement has got 2 units of precision. It's got 2 significant figures, 2 significant digits, because it's got both the ones and the tens position. So this number would have what I would say, shorthand, it has 2 sig figs, okay? 2 significant figures of precision. Now if I put that same object on another scale that is more precise, the measurement might register 2.473 grams. Now this number, the same object placed on this scale, is now being measured out to, okay, this position, 3 decimal places. Okay. Now if I were to round this number to the tenths, like the number above, we would still get 2.5. The instrument is rounding to that very last position. But this number now has got 4 levels of precision, 4 significant figures. Okay? And therefore, this instrument is much more precise. And when it comes to expense, it'd be much more expensive too. So you'll notice that the balance in my classrooms, for those of you that show up in my classroom, those balances that have housing where they have glass windows that you can slide open and shut, those measure out to 3 decimal places. The scales that we'll primarily use for the sake in this class will measure usually 1 or 2 decimal places, not nearly as much. And those don't usually have to have housings, but they're also much, much cheaper. Okay? So the number itself has different levels of precision. 2 significant figures, the top one versus 4. Okay? In any measurement in science, the very last number, like in 2.5, that number is a rounded or estimated value. The machine measured it at being between 2.4 and 2.5, but it was a little bit closer to 2.5, so it rounded it to 2.5. That last number in every measurement is always a rounded or educated guess. Let's take a look at this. I'm going to turn the page. All right, one last thing is sometimes along with measuring rulers in this class, the other thing that you'll measure is utilizing liquid volume. Okay, so the pictures down below here in the top two, these are graduate cylinders. Now on yours, you do need to make a change. The picture that I gave you was actually originally a burette, like you'll see below. I want this to be another example of a graduate cylinder. So cross off the 25 mark and put 23, 24, and 25. You'll notice that the scale in a graduated cylinder goes up. The 0 point is way at the bottom and its maximum value is at the top. The graduate cylinder fills bottom up, and therefore the measurements will go up as you go bottom up because that's how it's filled. Now when I put a liquid into a graduated cylinder, it bows. That bowing is said to be a meniscus. So when we record a liquid in a graduated cylinder or a burette, we always want to record from the bottom of the meniscus. Okay? So to take this measurement of the graduate cylinder letter A, you'll notice that we see there's the 50 line is here and the 60 is here. The 55 line is right here, and we have equal divisions. And if you count from 50 to 60, you'll notice that there are 10 lines. Because there are 10 lines there, I know that each tick mark, each mark is another milliliter of volume. 55, the mark right above it is 56. So I know the scaling of this graduated cylinder is to the nearest 1 milliliter. Because the scale is to the nearest 1 milliliter, I can now estimate one beyond that. So I know that my measurement here has got to be or be provided to the nearest tenth of a milliliter. So I look at the meniscus here in the picture, you'll notice that the bottom of the meniscus is right below the 53 line. The meniscus is between 52 and 53. So we always record the lowest value. So it's 52 point something. It's not right at the 53 line. If the meniscus was right on the 53 line, then I would say 53.0. But it's really close to it. I know it's more than halfway to the 53 mark, so maybe I would estimate 52.8 milliliters. If you had 52.9, if you had 52.5, I would give you credit for that because you've gone one beyond the scale. All right, now I said this was a burette, but if I change the numbers and make it a graduate cylinder, you'll notice now that 24 is here and 25 is here, and if you count, there are 10 equal divisions between 24 and 25. So this graduated cylinder would be recording to the nearest tenth of a milliliter. Because it's the tenth of a milliliter, I now know that I can record to 2 decimal places. That last one again will be the estimated digit. So I look at this graduated cylinder again, we always record from lower number to top number. So I always want to go bottom up. I'll notice that 23.5 is there, 0.6, 0.7, 0.8. Okay? I'll notice that, and it looks like the meniscus is right on that mark. Because it's on that mark, I know that it's going to be 23.8, and because it's right on it, I need to include that 0. Because the scale goes to the nearest tenth of a milliliter, my measurement would have to go one beyond that, or to the hundredths. So a better number for this object, this device that we'd use to measure, would be 23.80. If you think it's a little bit above that line, you might have put 23.81 or 82. If you think it's a little bit below, you might have said 23.79 or 78. But as long as it's around there and you have 2 decimal places, you're recording correctly. The other type of object that you might use is called a burette. And here is a picture of a burette. Now the difference with a burette is that when I fill a burette, we do not pour from the top out. We let the liquid drain out of the bottom. And because it drains out of the bottom, you'll notice that the numbers go down. Because the numbers go down, I always want to read from the smaller number to the larger number. So in a graduated cylinder, the smaller number is always below. I want to read bottom up. For a burette, because it drains out the bottom, I want to read top down in a burette. So when you look at these pictures, again, on your test for this unit in a couple weeks, you're going to have pictures and you're going to have to be asked which measurement will be the most closely to what it should be marked as. You want to first look at the scaling and see which way is it going. Always read from smaller to bigger, so I know I want to record moving down in the cylinder. Okay? Once I notice that, the next thing is to figure out the scale on the instrument. So again, you'll notice that this device goes from 40 to 41, and there are 10 equal divisions. Usually burettes are recorded to the nearest tenth of a milliliter. Each line is a tenth of a milliliter, which means I can visually break up between 1.1 and 1.2. I can visually break that up and record a number that is estimated one beyond that. So for both of these pictures, I would like you to record the number to 2 decimal places. If you need to pause the lecture briefly, write down your responses, and then click to play again and see if you get right about where I have it. Okay, so this picture is a little bit hard to read. 1, 2, 3, 4. So the 41 line is right there. And it looks like if I go this way, 41 and a half, 0.5, 0.4, 0.3, 0.2. It looks like it's between 41.1 and 41.2. And usually when it's hard to see, it looks like it's kind of roughly about halfway between. So I would say this is 41.15. If you had 41.11, 41.14, 41.17, as long as you had 41.1 something and you had that number to the second decimal place, you would get full credit on the exam. This next picture is a little bit easier to see because of the fact that it's yellow, but you'll notice that the meniscus looks like it's right on this 20.0 line. And again, you'll notice that there's 10 divisions between 19 and 20. So again, the scale is to the nearest tenth of a milliliter. Because it's right on the 20.0 line, I would say 20.00 milliliters. Now, some of you would see this picture, and I can guarantee you in the data table, you'd put down 20 milliliters. Some of you might put down 20.0. But to be perfect, the best measurement and what we should use based on this instrument is 20.00 milliliters. Most graduated cylinders in our class measure to the nearest 1 milliliter. Burettes measure to the nearest tenth of a milliliter. Guess which device is much more expensive to purchase? You're right, the burette. Burettes are much more expensive because they give you more precision in measuring the liquid. Okay? Also, you'll notice that the column thickness, the skinnier a column gets, the thinner its cylinder is, the more precision the measurement takes. And therefore, any glassware, the skinnier it gets, the more precise it is in measuring liquid volume. And therefore, we tend to be able to measure to more and more decimal places. But it also tends to be more expensive as well. All right, so you have now a homework. So today you're supposed to listen to this lecture. Tomorrow you have a homework which will review scientific notation from last week and then recording and measuring with different devices that I have. I've got pictures, again, of graduated cylinders and burettes, and I have also pictures of centimeter rulers or just rulers in general. And complete it. You can either annotate on the screen or you can print it off and fill it out and then submit it. This is a homework that I will be checking for accuracy because it's so important. These next couple of homework assignments I'm having you to submit this week just because of their importance leading into the exam, which looks like it's going to be at the end of next week. Okay, if you have any questions, please don't be afraid to send me an email or chime in one of my office hours, and please ask for help if you need some assistance. Thanks for listening. A blank canvas here. What I drew right here is an example of 2 different rulers. The top ruler, the first thing whenever we take a measurement in science is we want to know what each little mark represents. So if you notice here in the ruler, if this is a centimeter ruler, that it's going from 0, 1, 2, 3, but there's a mark in between, and this is representing the half measurements. However, if the instrument is not being broken down into sets of 10, okay, it's not being broken down in sets of 10, we cannot gain a level of precision. We can notice that this object above is between 1.5 and 2 centimeters. But I can't say that it's like 1.75. I can't guarantee that number is right there at the 3/4 mark because there's no mark given. So it's between 1.5 and 2. So a logical answer to this might be 1.6 centimeters. Someone else might say 1.7 centimeters. Someone else might say 1.8 centimeters. Neither of these three students are wrong. And they're also doing it correctly in the fact that this ruler will allow me to estimate to the tenths of a centimeter. And therefore, all these numbers would have two significant figures. It would have both the 1 is known, we know the object is at least 1 something, and then the second digit is the estimated value. And 1.6, 1.7, 1.8, these are all correct and valid responses based on how big this object is. So that would be two significant figures. Now, if this same object was placed next to a ruler where there is 10 divisions, we can notice right now that the edge of this is between 1.6 and 1.7. Because there's 10 equal divisions, that object, I can't count. It's between 1.7 and 1.8. And we'll notice that that object comes through here, like here. And let's say the 1.7 is here, the 1.8 is here. I can now visually break this scale up between 1.7 and 1.8 and say, okay, halfway between is about right here. So based on that, where that object is, it's not quite to the halfway mark between 1.7 and 1.8, which would be 1.75. So what I might say is I might estimate and say this object is 1.74 centimeters. Maybe you'd say 1.73. But because the scale goes to the nearest tenth of a centimeter, I know for a certainty that it's 1.7 something, and that last number again is estimated because I can visually break it down and say, okay, is it about halfway? Is it right on the 1.7 marker? Is it at the 1.8 marker? Okay, that's something that I would have to look at. So for the sake of this, I said it was about 1.74. So in every measurement in science, the very last number is an educated guess or an estimated value. We're rounding it to the nearest value that we think it may be. This number now has got three significant figures. So the same object, okay, I might have measured to be 1.7 centimeters with the top ruler. With the next ruler, I was able to measure to 1.74 centimeters accurately. I've gone from two significant figures to three. The instrument is more precise, and therefore I get a number that contains more significant figures. One last note on this. If you get to a ruler, let's say that it's 2.0, here's 3.0, and there are 10 equal divisions. So the first thing you should always do is figure out the scale. The scale of my instrument is measuring to the nearest tenth of a centimeter. The first job is to figure out the scale, and then you have to understand that when I make my measurement using this ruler, that I have to measure the number to the nearest hundredth of a centimeter. I always go one beyond the scale. Now, for some of you, you're like, who cares? But for those of you that really take a note to this, the instrument, okay, we will have a few questions on your quizzes and tests, and the key to get them right is you have to understand what the scale is. What do each of the marks represent? Up above, because the scale was not broken down by sets of 10, I could not say that that was like 1.75. I'm guessing at both the tenths and the hundredths position. You can only go to one estimated digit beyond the scale. So whenever you take measurements, that's what you have to be able to do and record. Okay? Now what happens if an object were to land right at the 2.5 line? Because the scale is to the nearest tenth of a centimeter, if I just said 2.5 centimeters, that is not correct because I've not gone one beyond the scale. I know that it's at least 2.5 centimeters, but because it's right on the line, I can add a 0 because that's telling me that that object that I'm measuring is right on the 2.5 line because I can go one beyond the decimal place. It's pretty easy to figure out how many decimal places you need when the object is between two tick marks. It's a lot harder when it's right on a tick mark, because you've got to be able to figure out what the scale is and what's one beyond that. It's even harder when you would have an object that would come right at the 2.0 line, because that line is at 2.0. Since it's right on the 2.0 line, I have to, again, put that extra 0 there, because that's my estimated digit. I'm assuming that that mark, that object, ends right at the 2.0 line, and therefore it's 2.00, and that last O tells me it's right on the 2.0 line. So no matter what I use this ruler to measure, you'll notice that all my measurements are to the hundredths position, because I've gone one beyond the scale.